It's April 17th, 2013, and this is the Energy Education Podcast. I'm Kevin Hurley. This week, we're talking about nuclear power plants that are too big to fail. It's common public perception that the sheer size of a nuclear power plant means that it must be safe. How could something so big and so heavy possibly budge? Of course, regardless of size, nuclear plants require tremendous quality assurance, upkeep, and maintenance. And despite the industry's best efforts, a number of plants have suffered catastrophic failures. We'll talk about several of these plant failures. Joining us to discuss is Arnie Gundersen. Arnie, welcome to the show.
Hey, Kevin. Thanks for having me again.
So today we're talking about nuclear power plants that are too big to fail. There's an illusion that nuclear power plants and their size and all of the quality assurance that goes into keeping them up, how could these things fail? They're so maintained and so large.
Yeah, there's actually two illusions there. The first is the sheer size. I've been on tours with people, and we used to deliberately take people on tours because they're so big and so impressive. And, frankly, your ego as a human being to create something this huge creates a sense of invincibility. There's a hubris that sets in the nuclear industry that these things are too big to fail. The second misconception there is all this high quality. Years ago, back in the 80s, I had dinner with a guy named W. Edwards Deming. And Deming is the guy that invented modern quality assurance. And he's there's a Deming Prize that the Japanese give for people that do high quality work. And so I was talking to Dr. Deming about nuclear, and he laughed. And he said, you're right. He says these nuclear plants think they have quality assurance programs, but they really don't know anything about it. The reason these power plants are so big is because the forces they have to contain are so big. The reactor core at Fukushima would have about 2,500 megawatts, and that's a mind-numbing number. It means nothing to the average person. But if you convert that over, that works out to be about 3.3 million horsepower. So if you put 3.3 million horsepower in something about the size of your bedroom, you get the feel for the enormous amount of power that has to be constrained. We used to take farmers on tours of our nuclear plants, and they'd probably be thinking in the back of their mind that, wow, this is a lot stronger than my barn. But their barn didn't have to hold 3.3 million horses either. And when we look at the size and we forget the magnitude of what we have constrained, the hubris sets in and we get to the point where we think we can conquer Mother Nature.
So we're looking at reactor containments that have walls that are, 12 inches thick, 2 feet thick? I mean, how could that possibly give?
Well, just this year, a nuclear reactor was permanently shut down, Crystal River. And no, it's not 1 or 2 feet. It was actually 40 inches thick, 3.5 feet thick.
The wall of the containment.
Yes, the wall of the containment. And the people that built the reactor were in the process of upgrading its power. And they had to cut a hole in the side of this and put in a new steam generator because they were engaged in something called an EPU, Extended Power Uprate. Dave Lochbaum, a Union of Concerned Scientists, calls those experimental power uprates because we really never know what's going to happen. Well, in the process of cutting the hole in this containment, it cracked, and it cracked big time, 60 feet around the containment and 20 feet high, and you could hear it. It was like a gunshot. Then they tried to fix it, and again, all this massive quality assurance, and the Nuclear Regulatory Commission was involved, and they started to tighten this containment back up after fixing it, and it cracked in 2 other places. So, all the king's horses and all the king's men sometimes can't put together a nuclear containment once it cracks. We sort of have a deep in our soul understanding that things fail. I mean, it can be the Titanic. It can be Bhopal, which was a chemical explosion years ago. It can be Chernobyl or 3 Mile Island. We know it has happened before, but yet our policymakers moving forward look at these plants and they say, how can something so robust fail again? We have to have learned all the lessons there are to learn. And I really think Chairman Yasko's comments last week really touched on that big things fail in big ways. And just like the banks in Wall Street, they are not too big to fail. We learned it on Wall Street. And it's a lesson that Americans think happened in Japan but can't happen here.
So we're talking about why big things fail. Now, I should think that it's not only due to the way that these big things are operated, but due to the way, human error in the way that they're operated, but due possibly also to human error during design and construction.
Yeah, I think there's 4 ways that these things fail. First is they're getting old. And I know I'm getting old and I'm breaking down more often, so why shouldn't we expect a power plant to do that? And some of the more recent failures have been because of aging. Second thing is that engineers make design calculation errors. And despite quality assurance overviews, they don't get caught. The third is operators make mistakes. And I really don't like to second guess operators with all the information that's going into their brains. They're bound to make a mistake periodically. And the last is that we can't forget that these things are built with a profit motive in mind, so that there's a increasing emphasis on squeezing more power out for less money.
Cutting corners.
Yeah, cutting corners.
So I know if we're talking about a 1970 Volkswagen and trying to replace the parts in it as it ages or keep it up to date as it ages is a tough thing. Can you just give us some idea of the enormity of trying to keep up an aging power plant, something that's this big?
Well, the average nuclear plant has 6 guys on eBay trying to buy old parts. And the reason for that is that if they put a new part in and it isn't a like-for-like replacement, they have to go to the Nuclear Regulatory Commission and ask permission. So they literally have a staff at every nuclear power plant of people scouring eBay looking for old parts so they can put those old parts in their warehouse. When one of their parts breaks, now they can replace in kind as opposed to going out and getting something better or newer.
But what we're talking about is really how big these plants are and the perception that they can't fail being, as big as they are. But as they age, and considering that they are so enormous, I would imagine can't be just as easy as, having your 1970 Volvo tuned up.
Yeah. There's very few people on the planet who can move the kinds of weight that are involved in building a nuclear power plant. An example, forget the old reactors. There's a brand new reactor being built in Georgia at Vogtle. And the nuclear reactor vessel was built in China or Japan and came over on a boat and made it to Savannah. And they put it on a railroad car that had hundreds of wheels. And the plan was they would pull it by rail the last 100 miles to the site. Well, wouldn't you know it, now this thing is enormous. You may have seen pictures of them. They're called Schnabel cars. And the track collapsed from the weight. Engineers had gone over that track with a fine-toothed comb, expecting that this could happen, and they missed it. Now, that's not safety-related. It's not built yet. But it's not necessarily something because they're old. I mean, here's something brand new. And literally, the nuclear renaissance was derailed in Georgia.
So how about some other examples of large nuclear equipment failures?
Well, in the last 2 months, we've got the 2 down south. The one was this Schnabel car, the Port of Savannah, that's gone off its rails. But the other one, tragically, was that in Arkansas, at Arkansas Nuclear 1, Unit 1. And there, a heavy component, not associated with the nuclear side, but the electric generating side, weighed 500 tons, that's 1 million pounds, was being lifted, and the crane failed. Now, if you look at the pictures of the crane, it doesn't look like it buckled from the weight. It looks like it toppled sideways. There was some kind of a lateral force on the crane that caused it to collapse sideways. And tragically, there was somebody under it when it fell, and so we have 1 fatality and 8 injuries. So there's 2 examples of non-nuclear, non-safety related, but still components within the nuclear plant that people just didn't analyze correctly.
So, of course, the nuclear industry is saying that this is an accident that was not a nuclear accident. It wasn't on the nuclear side of the power plant, and it's not safety related. So what does that mean? How are we to interpret or take an accident like this happening at a large plant? Should we be worried about it if it's really just not a nuclear accident?
I've heard people tell me that too, and I say, the same people that did that design calculation for the crane that collapsed at Arkansas are the same people doing the other calculations within the nuclear safety-related stuff. So if they can screw up on the non-nuclear side of the plant, they can certainly screw up on the nuclear plant. So I think failures like this, certainly they're tragic. But they also show the weakness in that we've got teams of engineers reviewing everybody's calculations, 3 times to Sunday, and they are still missing critical flaws.
But I would think the NRC reviews all of these calculations.
In congressional testimony back in 2007, the NRC admitted that they look at less than 5% of all the calculations that go into a nuclear plant. And there's numerous cases of when they did review, they missed it too. There was a failure in 2001 at Quad Cities, which is in Illinois, where a steam dryer, it's as big as a house and it's made of stainless steel and beautifully welded, cracked in an extended power up rate. There were indications that it had cracked, but they ran it and then they opened the nuclear reactor up and they said, oh my God, look, it's cracked. So they shut down, they hired every expert available, and they came up with what caused it to crack and the repair scheme. And then they contacted the Nuclear Regulatory Commission, and the Nuclear Regulatory Commission signed off saying, you did a great job. Well, they started Quad Cities back up, and it failed again. So they opened it up, and it failed worse. This time it sent a piece of steel about the size of a man down a main steam line, and it hit a reactor isolation valve. So the concept that, the NRC has looked at this, it's good enough, is just not true. And we've seen that elsewhere too. We've seen that at San Onofre, where the steam generators failed catastrophically. Well, in 2009, the NRC claims that they reviewed those calculations and couldn't find anything wrong. Well, if we're counting on the Nuclear Regulatory Commission to catch these, our faith is misplaced. There's only 2 inspectors at each nuclear plant, and there's 700 employees. So 700 employees can do a lot more calculating than 2 inspectors can check.
So, Arnie, you've talked a lot about design bases and whether or not the world's nuclear power plants are actually built to withstand the most that Mother Nature can throw at them. But doesn't this all rely on the quality assurance and the maintenance of these plants really being up to what they should be anyway?
Yeah, that's a really good question. First, the point is that if a nuclear plant went out and contacted independent experts about what the worst earthquake was or what the worst storm was or whatever, it's likely those independent experts would pick a number that was too high and too costly. So there's always in the back of management's mind, what's this going to cost? So there's a downward pressure from a cost standpoint to minimize what Mother Nature can throw at you. But then once that number's picked, we call that the design bases, now you're counting on engineers to do the calculations correctly. And the example that's ongoing right now is out at Fort Calhoun, which is on the Missouri River. Well, the Missouri River flooded, and the plant's been shut down for 2 years. And when they got into looking at their calculations that are 40 years old, they found they were missing, they found they were incomplete, and the ones that they could get their hands on were wrong. So for 40 years, this plant's been running with missing, incomplete, and wrong calculations. And that holds for all of these plants. They're all designed in the 60s and 70s and built in the 70s and 80s. So we're counting on engineers with slide rules in the 70s, and I was one of them, having done the calculations correctly. And it's critically important that they don't go back and look at those. Once the book is closed, the utilities don't want to go back and revisit that. Because if they find an error, that opens up a can of worms that nobody wants to get involved in, because then it calls into question everything else. So they call that grandfathering. And once these calculations have been done and signed off, then you're not allowed to go back and look at them again. It turned out at Fort Calhoun they had to, because there were some structural changes they wanted to make, and they had to find out the original design bases. They said, oh my God, these things are wrong. How many other plants around the country have that problem and are either haven't found it or have found it and are ignoring it? The people at Fort Calhoun knew these calculations were wrong for 10 or 15 years. And because they never needed to access the calculation, they could pretend that problem didn't exist.
So then, in a way, the Fort Calhoun plan is sort of like the too big to fail Death Star. Just, people had perceived it as so big and not able to withstand any kind of problem or attack.
Yeah, in fiction we all have the example of Star Wars and the Death Star, and it had a critical vulnerability that Luke Skywalker was able to exploit. Well, any system has a critical vulnerability. It doesn't have to be fiction. We learned that. We should have learned it at Fukushima Daiichi. And, as I've been saying all along, sooner or later, in any foolproof system, the fools are going to exceed the proofs.
Well, Arnie Gundersen, thanks for joining us again.
Thanks for having me, Kevin.
Well, that about does it for this week's show. You can catch us back here next week and every week for more on what's happening in the world of nuclear news and more technical nuclear discussion. Also, don't forget to like us on Facebook and follow us on Twitter. For Fairwind's Energy Education, I'm Kevin Hurley. Thanks for listening.
The second misconception there is all this high quality. Years ago, back in the 80s, I had dinner with a guy named W. Edwards Deming. And Deming is the guy that invented modern quality assurance. And he's there's a Deming Prize that the Japanese give for people that do high-quality work. And so I was talking for having me again.
So today we're talking about nuclear power plants that are too big to fail. There's an illusion that nuclear power plants and their size and all of the quality assurance that goes into keeping them up, how could these things fail? They're so maintained and so large.
Yeah, there's actually two illusions there. The first is the sheer size. I've been on tour.
It's April 17th, 2013, and this is the Energy Education Podcast. I'm Kevin Hurley. This week, we're talking about nuclear power plants that are too big to fail. It's common public perception that the sheer size of the nuclear power plant means that it must be safe. How could something so big and so heavy possibly budge?
With people, and we used to deliberately take people on tours because they're so big and so impressive. And, frankly, your ego as a human being to create something this huge creates a sense of invincibility. There's a hubris that sets in the nuclear industry that these things are too big to fail.
Of course, regardless of size, nuclear plants require tremendous quality assurance, upkeep, and maintenance. And despite the industry's best efforts, a number of plants have suffered catastrophic failures. We'll talk about several of these plant failures. Joining us to discuss is Arnie Gundersen. Arnie, welcome to the show.
Hey, Kevin, thanks.